Hello, this talk is going to give an overview of one of the tools we use to eliminate memory errors. So a little bit of a background. There's a few other solutions that we can use, Valgrind, electric fence, some debug runtimes and address sanitizer. Now there's a few issues with some of these. For example, Valgrind runs a little bit too slow, so for our kind of real-time or interactive simulations it's just a bit painful to use. Electric fence generally only deals with heap issues. Debug runtimes is alright on the compilers that support them. And address sanitizer is actually pretty good. We do use this. It's annoying that it's taken so long to appear, and there are occasional compilers we use that unfortunately don't support it, and likewise platforms. But no, address sanitizer is actually very good. I recommend it. But what we actually have is libstent, and what it provides is effectively a weak pointer for C. And the good news is that we can strip it out during our release builds, and it pretty much has no cost in terms of overhead or anything like that. It also provides a few other things like a templated vector for C, so a type-safe dynamic kind of container. And it's basically a single header file. And of course C89 compatibility, which is, I don't know, it's more of a novelty than anything. I think everyone's pretty much on C99 at the very least. So what we'll do is I'll actually take you through some code showing how it's kind of integrated. So what we've got then in this directory, we've got the make file, a main.c file, that stent header file, and let's have a look at the code. So currently it's pretty basic. All we're doing is creating an employee structure. We're kind of allocating it with calloc, so it's like 0 initialized. Then we're freeing it. Now what I'm going to do is I'm going to add a problem. So I'm going to do emp id is 9 after the free. Now it may or may not give an error. This is the whole problem we're trying to avoid, basically. So if I run it, can you see it actually ran to completion? There was no error. It returned 0 effectively to the operating system. So it got to here, and that's a problem because sometimes it obviously might kick out an error. And to be honest, it would normally kick out an error while doing presentations, just not this one, obviously. So what we're going to do is we're going to now, instead of using raw C, we're kind of going to use that stent system. So let's include it. Now because stent is a single header file, similar to the STB image stuff if you've used that, in one unit you have to have a define before you actually include it, so it actually puts the actual C code there. So I'm going to do define stent implementation, and now in this one unit it'll actually put the implementation of stent there as well. It's just a way we can get it into a single header file. And let's modify this stuff a bit so that it's suitable for stent. So what this means is we're going to wrap this employee structure pointer into a ref type. And instead of using calloc and the size of emp and all that stuff, it's going to be allocate and then employee. And instead of free, it's going to be release. And probably one of the most, I guess, not annoying, but kind of invasive kind of parts of it is, in order to access member variables, fields, I guess, we need to have this underscore almost macro around the actual type, variable, sorry, because that's how it checks each time it's accessed. But to be honest, it's not that much longer, because if you get rid of the arrow and you replace it, I think it's only an extra character longer. So now if we run this, and I run it, can you see it's reliably crashed? I mean, I might have just got lucky, but effectively now, from now on, it permanently will pick up that as an issue, and it will tell you the actual source file and the line number. and if I kind of release it after we access it, it should run to completion. So that's all well and good. And if I forget to release it, so if I just comment this out for now, you'll see that we've actually got just an output of a memory leak, which is quite handy. So again, it actually says where the memory was originally allocated, which actually ended up leaking. And it also says the type, which is quite convenient, to be honest. So that's pretty much how you can convert a raw C program to one using Stent. This slide's pretty much just detailing what I did. The accessing members, yep, so it works pretty much same way as I showed. So you've got the _emp, and then you can use dots instead of the arrow to dereference it. And then you can pretty much just treat it like normal. Likewise, to actually read the data as well, you can also just use it as shown here. So again, as I demonstrated, it also gives leak output. And then the most important though is the use after free. Just because this I notice is just so awkward to debug. I'm sure you've all encountered it, and it can also just cause issues somewhere much further in the program that just makes it a bit of a nightmare to debug without tooling. Now, if I go back to this one, you might just say that this release could be a macro that not only just calls free on emp, but also just sets emp to null. And that's actually a strategy that a lot of people use. That once they free it, they simply set the variable to null. But as you might guess, what happens if you've actually got two references to that data? If one of them's deleted, the other one is left dangling. Now, Stent works in a bit of a different way in that it will pick that up. So if we demo that here, so let's say I've got this other ref variable, so ref employee, and we'll call this global emp, a bit naff, but we'll go with it. And so we've allocated emp. Now I'm going to simply set global emp to be emp. So now emp is pointing at the data and global emp is also pointing there. Now I'm going to release emp, and then I'm going to try to access the data using global emp. And if I run it, you can see it's giving us the same issue, same sort of like reliable error, hopefully deterministic. So employee pointer no longer valid in main C, line 21. And that's really handy, because obviously if you're kind of dealing with a large program, you may have many pointers to one bit of data. Now, some things that are quite handy, in structures you can also have this ref type. It really is just treated just like a pointer. And you can also pass it in as parameters, and likewise you can also return it as returns. And you can pretty much treat it in exactly the same way as you would just a normal pointer. So it's not really that invasive. And I'll show you a software that kind of uses it internally, so you can see that it's not too much of an issue. But the functionality is really handy. Now what's also quite nice is if you make sure to, instead of using raw pointers, you use this ref stuff for sort of like member data inside a structure, and you never use a raw pointer, it means that when you do come across a raw pointer within, for example, function parameters, you know that this is actually safe to use throughout the lifespan of the function, because you know it's coming from the stack, which is really handy. Obviously you could easily set it so you have it from a vector, which we'll encounter in a bit, but it's much better if you just make sure to have a little bit of discipline to make sure you only ever use raw pointers pointing to the stack. It just makes the whole code base a little bit more, I guess, robust. And having this way of using ref to kind of separate them is actually quite nice. So vectors, this is quite nice as well, in the fact that it hides a lot of things. Instead of having to deal with sort of like either linked list yourself or having effectively, multiple dimensions of pointers, it wraps it quite nicely. So I will actually demo this, just because it's not too bad. So we'll make an actual vector of emps. Now we could make a vector of emp pointers by using ref and then employee, but I'm just going to make it a normal struct employee. Actually, no, I'm not. I'm going to use integers, because otherwise it's a pain to push them back. So I'm going to call mine numbers and then equals vector new and then the type again. And effectively I can then do vector push and then the actual context and then the number to push. And let's actually let it leak. Let's not delete it for now. That looks about right. And you can see it worked. It says we got a leak, so the allocated memory persisted after the exit. That's all well and good. And if we want to delete it, it can just be vector delete. Cool. So vectors kind of use the same ref system underneath. So it means that effectively they can't dangle either. You can actually pass them around. So in, for example, C++, you can pass them around as references. You wouldn't generally want to copy a vector each time. But actually, these vectors, they're effectively pointers on the heap, so you can just pass them around just as normal. So I'll just show you that now. Test func, and it takes in a vector ints, and we'll call this ABC. So if I do test func ns, that then should work. Yeah, well, that function doesn't do a whole lot, but you can see it's quite handy just to pass them around like that. So moving on. So yeah, it doesn't just need to take in a primitive or even structure. It can also take in, the refs that I mentioned, which is quite handy. So you can push it back like this. This is what I wanted to avoid by using the integer. I didn't have that function set up. And then you can access data using at. I didn't really give an example of that. Let's do that now. So effectively it's just int val. And then we can just simply do val equals vector at the vector and then at index 0. So if I run this, val basically is now 9. If I chose an invalid index, so 1, let's say I just gone off by 1 error, and I run it now, you can see it's actually reliably again bombed out. So it's saying the index you requested is 1 and it's out of bounds because the size of the total vector is 1. So obviously index 0 is what we would have needed. So that's again quite nice, I guess. So what's this example showing? Oh yeah, so in this example we're deleting the vector, but we're actually forgetting to delete the employees that we pushed back. So this output is actually reminding us of that. So that's quite nice because effectively it would have been very easy to forget to delete these, certainly during this demo. So we can iterate through a vector quite happily using this for each. This is a macro that I made just because the alternative's a little bit long-winded, like a for loop. So here's an example just of iterating through it. So it's the type, and if I go back, you can see the type is a ref employee vector. So ref employee emp, that's the emp for the individual index. That's the vector emps, and then effectively you can do whatever you want with it. So you can use the underscore brackets thing to access the data of that emp structure. And then when you're done with it, vector delete. So this would be a quick way of actually just freeing each of those employees from the vector before you finally delete it. This is an example of how it would be without that macro. So normally I really hate sort of like these for each macros. I find them unnecessary. But in this case, because with C you kind of need to have the the variable defined at the very beginning of a block, I find sometimes it's a bit messy to have all these extra variables around. So that's why I made the macro. You can go with both, it doesn't really matter. So yeah, as demonstrated, it shows out of bounds errors quite happily, which is very nice. So here I'm just pushing back 3 and then trying to access the third one, so it bombs out. Pretty much showed you that. And we have additional vector functionality, so we can also use vector resize just to make the vector an arbitrary size, and it fills the rest of them with 0. Vector clear, which actually sets the size to 0 but doesn't set the actual backing store. It doesn't change that size, so future additions doesn't need to allocate anything. It keeps the actual memory. In some ways I guess that would be an issue if you're in like very memory constrained environments, but it should be fine for certainly our users. It's easy to change anyway. Vector insert, so you can insert an arbitrary amount of data from another vector into a single vector. This has been really handy when working with sockets and like buffers from all the data coming in. And then finally vector arrays to actually just delete an arbitrary amount of data from the vector. So this is all stuff that would be a little bit fiddly if you're just dealing with the raw memory. I know I kept buggering that up, so that's where I kind of started on Stent in all fairness. Some other stuff, we have a casting that's type safe. So you might notice when we use allocate, we actually pass in the type rather than the size, like size of whatever. And that means it actually does internally, it stores the type during the debug build, not the release build. So if in your debug time this cast fails because it's the wrong type, that's fine, you've done something wrong, and then you strip that all out in the release build and it's good to go, and it's as fast with no overhead, as long as you actually don't uncover a new kind of code path that exhibits the bug. So yeah, it gives you a nice error message. Some other bits, yeah, it's completely thread safe for the accessing. I don't know about allocating data. I don't think that's going to be thread safe. But generally, you'll see this in a little bit. I kind of line up the data. I very rarely allocate data in threads anyway. I know many use cases do require that, but that might be something to address. To be honest, it'd be fairly easy to put some mutexes around the certain areas, to be honest. It provides string, so this is basically string. I named it stream so it didn't conflict with string when dealing with C++ compilers. And yeah, it kind of works in the same way. It's really just a vector underneath, to be honest. Some very simple, very incomplete file handling just to kind of avoid the raw pointers. I've only kind of made it as I needed it. Same with the directory stuff. And again, this is just POSIX OpenDIR, so it won't work on Windows without a shim. So yeah, like I mentioned, we have this define. So if you undefine stent enable, it literally just strips it all out and it's as fast as before. And I'll show you a performance test in a sec. And so without that, pointers aren't checked. And really, just the macro underneath it literally just says a ref employee is just a struct employee pointer. That's literally it. When it is enabled, it's a little bit more complex. It's basically a struct employee pointer because it's got some additional, it's going to be a bit hard to explain without a diagram, but it's got an additional direction to like an allocation block, which then tracks whether it's already been deleted. And that underscore bracket macro is what goes through, does the check first before it accesses the actual data. And likewise, the vector bounds are no longer checked. That's really important, certainly for the, we have a project where it's basically a software rasterizer, and in release mode it's it's bearable. In debug mode, where it checks every time it accesses a pixel, it's a little bit slow. But I'll show you that. So these are some of our projects. This is actually that software rasterizer I referred to. We have network-aware implementation of OpenGL, which is basically just the OpenGL commands streamed through a socket. We kind of use libstent for that. We make a couple of games. Here's one where we kind of gutted some old World War II rifles to make some kind of shooting games for the visitors to a tank museum. And then this WebSocket implementation is just because we couldn't find a light one. I think the best we found was Mongoose from the Sysanta guys. That was light, but we just kept making mistakes of it because it's raw pointers everywhere. And yeah, so we need something a bit safer. I'm sure there are more competent developers that are fine with it. So before I go on to this, what I'll do is I'll show you some examples. So if I go into the Stent project, this is what's on GitHub, and if I go into the build, basically I've got a bunch of tests here. If I run ctest, it doesn't really mean much at the moment, but 17 tests passed. So these are different sort of like tests to just make sure that undefined or memory corruption bugs get exhibited, and it's basically managed to handle each one. Now if I go into the same build but libstent's been disabled and I run ctest, it's quite interesting because some have passed. They shouldn't have, but because it's undefined behavior, it kind of randomly works sometimes. Many have failed, and you can see it's actually frozen now because some memory's 0, and I think it's probably timesing it by something, so it's remaining at 0, so it's never counting up. I think that's what happened last time I checked. So it's actually in a constant loop, just doing nothing. Again, undefined behavior is great fun. So the test never actually complete, which is a bit annoying. I haven't fiddled with ctest to solve that. But you can see that many fail, basically. And let's now look at a software renderer. And before I show you I'll show you the code first. Let's have a look at the renderer. This is a random choice. So you can see here in the structure, the renderer unit, this is kind of what's running in a single thread. You can actually see Stent is pretty much in everything. So I've got refs, I've got vector for all the faces, I'm using it for a list of all the vertices, and again the actual renderer pointer is a ref. So it's very much using Stent for everything. I don't think there's any raw pointers in this whole project actually. And let's have a look at the performance. So if I run the debug, so this is it with Stent enabled basically. So okay, it's not great. I mean, it's not too bad. If I make it quite a small window, he does rotate. But yeah, the cat, he rotates kind of slowly. Now if I run the same project but with Stent disabled, you can see it's a lot faster. So it's not a brilliant test, but you can kind of see the slight overhead that Stent has, and you can kind of gauge its performance. I think it's a little bit slower than Address Sanitizer, the instrumentation that we add, but it works on any compiler, any C compiler. So there is a bit of a trade-off there. So that's pretty much it for that test. So yeah, if you have any questions, please send me an email. You're probably better off actually putting it onto the GitHub repo here. Just log an issue or something like that, or either way is good. So thanks for listening. Catch you later.